Okay, this is 0.2, and at 0.2, we're going to talk about real numbers. All of these things that you have listed here, and there's a couple more on the next page, they're all real numbers. And so all the real numbers can be encompassed into this here. And so I think of real numbers is like kind of mountain. You got to get up to the top of the mountain, you have to climb all the way up every other level of the mountain to get there, right? We generally just don't go, hey, I want to be on the top of the mountain, boom, we're there. So as we can see here, they're using this diagram, and we're talking about real numbers. And the real numbers are pretty much everything you guys have probably seen ever in your life. Now, there are such things as things that are called non-real numbers. They're called imaginary. You guys will get to that eventually. I think algebra 2 is when we first start to see those. That's what happens when you take a square root of a negative number. So from now on, we're just going to say we're dealing with the real stuff. The stuff that we can see and we can use. Now, real numbers are made up of these definitions here. So, positive numbers. What is a positive number? What's the definition of a positive number? What do we say are positive numbers? Positive numbers. Anything to the right of zero. I like that. So on a number line, right? On a number line, it's right of 0. So on a number line, remember, if 0 is here, we're talking about all the numbers on this side. Now, is 0 included on that? Did we say 0 is positive or 0 is negative? No. So we don't generally include 0. So I'm going to put a hole in the circle there because it's not included. We're not going to say it's positive or it's negative. Okay? Therefore, negative numbers are the numbers on the left. So the left of 0. And on that number line, if 0 is here, it's an open dot, and I shade to the left. Those are negative numbers. Remember, on a number line, as you go to the right, the bigger the numbers are. As you go to the left, the smaller the numbers are. Yes? That's big to remember. Now, natural numbers. What are natural numbers? They're all different things here. Positive numbers not including 0. So that's what I like. I like that. Think of it naturally when you start to count. When you started to count, when you were probably 1 or 2, somewhere in between there, your parents started having you count. They went, okay, 0, 1. No, they didn't do that, right? What's the first number you started on as a kid? 1. And then you went to 2. Then you went to 5. And then you went to 6 because you didn't know your order. But those are all natural numbers. Your natural numbers are your integers. We're going to call them integers now, granted, that's another definition down there. So, positive numbers, positive, we're going to call integers, greater than 0, 0, 0, not included. My handwriting is horrible. But it's positive integers greater than 0, and 0 is not included. Then we step into whole numbers. Whole numbers are the exact same thing as natural numbers, but what? What's included this time? 0. So these are the natural numbers. Natural numbers, not hashtag, including 0. So it's all the natural numbers, 1, 2, 3, 4, 5, 6, so on, and 0. So now we would start at 0, 1, 2, 3, 4. Integers, just like natural numbers, just like whole numbers, but they also include the negatives. So it's the positive and negative whole numbers. right? It includes -1, -2, -3. Basically, integers are all the nice numbers. Anything that you think would be nice that you would want to use in an equation or in the world, right? Unfortunately, not every number turns out to be nice. We got something called rational numbers. Rational numbers technically can be nice. 5's a rational number. But generally, when we think of rational numbers, we're thinking of the not-so-nice ones, and those would be like 3.2, 3.57, okay? So rational numbers, we sometimes say, hey, those are fractions, decimals. Now, this is, when we say decimals, they have to be of two types. They either have to repeat, so like 1/3, 1 divided by 3 is 0.33333333333, goes on forever, right? That's a repeating decimal. Or you have to have a terminating decimal like 2.5. So 0.5, it stops. We can write those as fractions. So rational numbers all can be written as a fraction in some way, shape, or form. Okay. Now, as we're looking at that diagram that's above, we talked about natural, we talked about whole numbers, we talked about integers, we talked about rational. Real is pretty much everything. The only thing that we haven't got on here is we didn't talk about the irrational numbers. I don't have the definition written on here, but irrational numbers are the ones that cannot be written as fractions. So we're going to squeeze that in here. Can't be written as fractions. An example of this, a big one that you guys all know of, pi. Pi is 3.14 and it goes on forever. It's a non-terminating decimal. It doesn't repeat itself. Another one of these is something like the square root of 3. So square roots, a lot of square roots happen to be irrational numbers. They don't seem to ever stop. But let's take a look at this diagram a little bit closer. This diagram starts off with this whole group of numbers that we call real. And within the real numbers, it breaks into two camps. There are the irrational numbers, or rational numbers, the pi's, the e's, the square roots that don't stop. And then it turns into real numbers. So, or not real numbers, rational numbers, sorry. So there's two sub-levels of numbers. So rational numbers is like the base of our mountain. From there, we can start to get a little bit smaller group, be more selective of what we want. Because as you can see that all rational numbers, there's something called integers. And integers are those nice ones, right? The nice -2, -5, -3, 0. And from there, we can be a little more selective and go to the whole numbers, which means I don't like negative numbers, so we're just going to get rid of the negatives. We just talk about 0, 1, 2, 3, and then we go to natural numbers, the stuff that we really like, because that's the way we learned how to count, 1, 2, 3, 4. So the most selective group of numbers are your natural numbers. They're like the top of the mountain. But here's the cool thing. If I am a natural number, I am also within the circle of a whole number. And I'm also in the circle of an integer, which is a rational number, which is real. So to be in the top of the mountain, you are all of the others. Does that make sense? So if I saw the number 2 and it asked me, what is 2? What kind of number is 2? 2 is a whole number. It's a natural number, then it's a whole number, it's an integer, it's a rational number, and it's real. You have to write 5 things down for that. If I said something like 4.8, well, it's not a natural, so don't say it. It's not whole, it's not an integer, it's a rational number. So it's a rational number and it's real. So that's what you would have to do for your homework. Okay, so example 1 there, I have 3 different numbers, and I want you to classify them for me. So I'll give you guys a second or two, write those down, and you guys try them. Tell me every single one of the classes that they're in. So, first one, 5 over 22. 5 divided by 22. Does it happen to be a nice number? Does it turn out to be nice? Does 22 go into 5 nicely? No. Now, here's a cool thing. We know it's not irrational because it's a fraction. If it can be written as a fraction, you know it's going to be rational. So, because it's a fraction, I'm going to say that, that it's rational. But since it's rational, therefore it also has to be what kind of number? What's the very broadest thing that we have? The very broadest thing we have is that they are real. So it has to be a real number, so you have to list that too. So it's real. It's rational. Now, since we said it doesn't turn out to be something nice, if I go back here, we know it's rational. Get my pointer out. It's rational, so therefore it's real. Is it an integer? Well, if it's not nice, it can't be an integer, right? So guess what? 5 over 22 is just those two. It's real and it's rational. Square root of 81, though. Can I simplify that? What's the square root of 81? So it's 9. Is that a nice number? Well, first of all, let's start. You can start either on the top of the mountain or the base of the mountain. We'll start on the base. Is 9 a real number? So we got to state that, real. Let's level up that mountain. Is it rational? Can it be written as a fraction? Yeah. So it's rational. The next one on the mountain is what? Does it happen to be an integer? Is it a nice number, positive or negative? Yeah, so it's an integer. After that, it goes to a whole number. Whole number just gets rid of all the negatives. It's a positive, so we're good. So it's a whole number. And is it a natural number? Is it one of the original counting numbers that you have practiced your whole entire life? Yes. So therefore, it is a natural number. Now, that was starting at the base of the mountain and going up. If we would have looked at the very, very top, and we would have said, is it a natural number right off the bat? And you guys would have said, yes. I learned how to count that way when I was 2 or 3. Therefore, all of the others would have just had to come along for the ride. If you state it's a natural number, then it's also a whole number, it's also an integer, it's also rational, and it's a real number. All of them go along. Okay? C, square root of 56. Is that a nice number? Put it on your calculator once. What is square root of 56? .48 ... It goes on forever. Therefore, can I write it as a fraction? Does it repeat? We look at it, it doesn't repeat. 2, does it ever stop? Oh yeah, Mr. Contract, my calculator stops right here, way over on 9 decimals. Guess what? That's not really stopped. Your calculator eventually had a round. This goes on forever. So therefore, it's not a natural number, because we can't count it. It's not a whole number, because it's not nice. It's not an integer. It's not, oh, is it rational? No, it's not rational. Therefore, because it doesn't repeat, it's actually irrational. But if it's irrational, it's still real. So part of your homework, guys, is to actually tell me or list all of the things that it is or can be. Those are definitions. What does it mean to graph something? To graph something is to put it on paper, right? It means to plot it. It means to draw or plot. So we're going to draw or plot the points. And we're going to plot these on a coordinate, or as a coordinate, on a number line. And so it corresponds, the coordinate is its place on a number line. So we talked about number lines a little bit, so we're going to draw one out here now. That as a number line, 0 is generally in the middle of a number line in a large scheme of things. Now, here's the thing. It doesn't necessarily have to be 0 always on our number line, because we might be talking about numbers like 100 or 200, and therefore 0 wouldn't even be in the neighborhood. But we got some general rule here, and the general rule says that as I go this way, the numbers get larger. This way, they get smaller. They're positive over here, while they're negative to the left. Right? We talked about that. And so that's kind of the idea here. Our idea is the fact that you're going to want to, if I wanted to say, I wanted to plot 5. Then if I wanted to plot 5, I can go 1, 2, 3, 4, 5, put a dot at 5, and I'm going to mark it and say that's 5. I do not need to mark every tick mark as I go along. I can count that. Now, if I'm going to go by 2s, like I want to call this 2, 4, 6, well then I just have to list that first one. Whoops. That first 1, 2, well then obviously this would not be 5. 5 would not be there. 5 would have to be here, right? Because I'm going by 2s. So, however you make your scale, you need to tell us. If you don't tell us, we default and say every tick mark says it's 1. Now, what we need to do here is we need to graph an order. So you're going to put all of those numbers. We'll do the first 1 or 2 together. I have some steps for this to do this. What we're going to do is we're going to graph and order these. So write these down. Okay. As you're writing those few things down, this is what we're going to do. Number 1, steps to putting these in order and plotting them. The first thing I want you to do is I want you to convert to decimals. I want you to convert to decimals because we know how to compare decimals. 1.2 is bigger than 1.1. And so everything needs to be converted to a decimal. So you need to take your calculator out, and let's look at the first ones. Now, some of these, though, because they all have common denominators, actually we don't need to convert, but we're going to do it anyways. What's 5 divided by 3? 5 divided by 3 is about 1.6 repeating. Negative 4 divided by 3 is definitely going to be negative. Negative 1.3 repeat. 2 divided by 3 is 0.6 repeat. And a negative 1/3 is a negative 0.3 repeat. These are not nice numbers that when we go to make our number line are going to fit on there perfectly, right? We're going to have to approximate things. What's our biggest number? Just by looking at that, what's the biggest number? Our biggest number is 1.6, repeat. Our smallest number, or the biggest negative, is negative 1.3, repeat. That means when I make my number line, I'm going to accommodate for that. I'm going to make this number line, and I'm probably going to put 0 in the middle. I don't have to put 0 in the middle, but if I make this 1 and 2, 1 and 2, I can go up to negative or positive 2 and negative 2. Now, I said I don't need to do this. I'm doing this for this one, so you can kind of see your numbers. But I list them as 1, 2, -1, -2. I'm going to plot my points. So we converted them all to decimals, and 2 plot on number line, and 3 rewrite in order. When we say order, we're always usually talking the smallest to largest. So, I'm just going to go left to right, plotting my points. 1.6. 1.6, we're just kind of round in there a little bit. But 1.6 is bigger than 1, but less than 2. So if I had to, I'm going to place it somewhere in here, right? But 1.6, 0.6 is bigger than halfway. So that means I'm going to go over a little over halfway there and put a point at 1.6 repeat. Notice that underneath it, I'm going to label my point so that I can see where my points are, which ones are furthest along than the others. -1.3. -1.3 is going past -1, but am I going more than halfway or less than halfway to 2? To -2, sorry. 1.3 is less than halfway, so I'm probably going to be somewhere about here, about a third of the way. And this becomes a -1.3. Then I go to 0.6, and that's a little over halfway between 0 and 1. Oops, wrong one. So 0.6, and -0.3 is less than halfway. Repeats, right? So now that we have them plotted, looking from left to right, I just write my points down. And then those answers will be -1.3 repeat, comma, -0.3 repeat, 0.6 repeat, comma, 1.6 repeat. Right? I just put them in order. Now, there's a couple extra steps in here. I'm converting to decimals. I'm plotting them. And then I'm putting them in order. But here's the problem, or here's the thing. The original problem was not given to me in decimals. So should I use those decimal answers as my problems? Or as part of my solution? No. I want you to change them back. Now here's the thing. Notice this order here is the same as that order up there. So you know which one applies to which fraction and decimal. 1.6, or -1.3, our first number, is the second number. So -4/3. -4/3. -0.3 is the last one. So it's a -1/3. And then it goes to 2/3 and 5/3. That is your answer. Convert them back to the original problems. Okay, so now we're at the point where we're going to talk about the systems. Guys, there are 3 types of systems that we're going to deal with. We're going to deal with systems of equations that will cross. They have a name for it in this book. This book, we start to say, hey, we have a system here that is what we're going to call consistent. This is what we call consistent. And we call it independent. Whoa, that's bad. Independent. It's independent because there's only one solution. As you can see, that the system will cross, right? And everybody should be able to say, hey, right here, those two lines intersect, forming one solution. And if there's only one of you, that means you're pretty independent, right? So, one solution, maybe put above here, one solution. So when you go to graph it, now what we're going to do is we're going to take more than one of those equations. Now in your homework, I only asked you to graph one of them. Now we're going to start to graph both of them on the same graph and look for where do they intersect. So there's one solution, and if there is a solution, that means there's things being pretty consistently. We're coming up with a solution. And that solution, since there's only one, it's independent. It's on its own. Another situation that we're going to come across, and again, there are three of them. So I'll just draw two more of these, is what happens if you draw it, and you draw both of your lines, and all you're looking at the graph now is you only see one equation. You only see one line. That means that your lines are stacked on top of each other, right? Which means they're the exact same line. How many points do they have in common then? This one's only got one. If their two lines are stacked on top of each other, how many points are the same? All of them. So this one we call infinite many solutions because there's always another solution that's exactly the same they have in common. This is still consistent. It's consistent because there's an answer. Here's the thing, though. There's not just one of them. There's many of them. And when there's many of them, you're generally dependent on each other, right? So this is going to be dependent. This is dependent. So we get infinite many, it's consistent, and it's dependent. The last one that we're going to have is if you have lines that never touch. Lines that never touch, is there ever a solution?
No.
No. So this one, say is no solution. If it has a solution, it's consistent. If it has no solution, it's inconsistent. And we don't have to say anything about dependent and independent because it only depends dependent and independent when there is a solution. Okay, so we're just going to come up with problems and they're just going to give you a graph. And so you're going to graph your problems and see a situation like this. And you'd be like, oh, that's infinite many solutions. It's consistent, but it's dependent. That's what you would say. Or you would see only one solution because they're crossing out in the middle of someplace. And you would say, oh, there's one solution. It's consistent, but it's independent. It's on its own. We're not stopping there. Because if there is just one solution, like the top example, you need to name it. Where is that point? Is it at 5, 7? Is it at -2, -3? Okay? So your goal, guys, is to use that information that we just did before with graphing your equations together this time on the same graph and look for on that graph, where do they cross, if they do. And if they cross, you tell me. They cross at this point. Remember, it's always x, comma, y, right? So are there any questions to that? So on this example, I'm giving you just the graph. I'm giving you equations. Tell me, how many solutions? One. Because there's one solution, we say it's what? Independent. It's independent, and we're also going to say one solution, it's independent, and consistent. I also want you to stay, because there's one solution, tell me what it is. Here's the thing. This is my graph. Is it going to be accurate? Maybe, and maybe not. So there's going to be times, guys, you guys are going to say yes with your graphs, and you're going to say, oh, it's at 1, 2, and then you check the back of the book, and it says it's 2, 3. And you're like, oh, I did it wrong. No, you didn't necessarily do it wrong. It's just that your graphs have error. And so your graph might not be perfect. And so therefore, I'm not asking you to regraph something. I'll ask you to check it. And if you're wrong, it's okay. There's better ways to find right answer. So if I was going to ask you where the solution to this lies, where would you say it lies? I think all of us would guarantee, or we'd say it's at that point. But what is that point? What's that? 3, 3? Is everybody going to agree with that? That's 3, 3? I mean, I think I could force it to be 3, 3, right? Maybe 3.25, comma 3? Would you guys necessarily be wrong? No. Okay? So 3, 3 is okay for me. Solve this system by graphing, which means graph each equation on the same graph, look for where they intersect, name the point. I'll give you some time. How many people are like, oh, this is in standard form. I'm going to the eye doctor and using cover up. I put my points there. We talked about this. Put a 0 in for x's and for the y's. I'm doing this twice because there are 2 lines in standard form. So the top 2 points are for the first line. The whole idea here is to solve for the x and y intercepts. The first one says, put a 0 in for x. When I do that, it's gone. Look at that, it's magic. I disappeared it. So y equals 2. I can make y disappear, so x equals 2. And so I have now found the x and y intercept over the first line. Remember, when you're plugging zeros in, it makes them disappear. You guys remember this? So I'm going to do the same thing with the second line. If I put 0 in for x, 3 times 0 is 0, and I really don't have to write it anymore. So when does 2y equal 9? Divide both sides by 2. 9 divided by 2. We got a calculator. What is it? 4.5. Do the same thing. Put a 0 in for y. That makes this y part disappear. Divide both sides by 3. X's. What's 9 divided by 3? 3. Whoops, whoa. 3. Can I plot those points? Can I connect them with a straight line? Yes. That's the wonderful thing about this. I'll tell you this. make your graphs with straight lines, you're going to be happier. Try to be as straight as we can with our lines, because if you're not, your graphs get off, and then everybody's like, and again, make your tick marks as evenly as possible. So, I'm going to graph the first one, 0, 2, 2, 0. Is everybody okay with that? And I'm going to draw my line. There it is. The next one, 0, 4.5. 1, 2, 3, 4.5. And 0, what? Or not 0, but 3, 0, which is there. So now I have to draw my line here. And that's another thing, guys. You have to draw your graph big enough for you to actually see the line, a point of intersection. And I think most of us would agree that the point of intersection is there. All you have to do now is name it. So, this is obviously one solution, which means it's what? Independent. And consistent. And the point happens to be, at least on my graph, yours might be slightly different, right? I get maybe 1, 2, 3, 4.5. 4.5, comma, 1, 2, 3, 4. Negative 4. Is that what everybody else got?
I got 3.51.
3.51.
And negative 1, yeah.
Wow.
I must have had a really bad graph. But
Okay. Is that what else got? Pretty sure everybody got something slightly different. Here's the thing. I want you guys then to take the answer that you got, that's mine, and plug them back into the equation. It should work for both. All you have to do then is just check it. So for me, I need to take 4.5 minus a negative 4, and that should equal 2. Ooh. Oh, guys, we made a mistake. Made a mistake. No one caught it. What was my mistake? Made a mistake. Okay, guys, we're going to fix this real quick, but we're not going to change your numbers. Leave your numbers there. What we had here is, when we did our cover-up method, this y value should be a negative here. And so to fix that for us real quick and make it so we can just keep our numbers going, let's just change it to x plus y. That way, if we use my numbers up here, which did everybody use those numbers? We'll just keep it consistent. Okay? So which means I would have to add these together. But 4.5 plus a negative 4 is 0.5, and that does not equal 2. So therefore, my point is not the solution. I'm not going back and fixing it. I don't expect you to go back and fix it either. I just wanted you guys to get the idea of graphing, finding a point, and being able to identify independent, dependent, consistent, inconsistent, how many solutions. The next section or so, we're going to find the real solution, the easy way, the right way.